Hello, Tyler.
Hey.
It's so good that you could be in Munich this day, and we have so many questions to you. We already had some correspondence in the last year.
Okay.
I printed it out. It's almost a book, and now you will take the rest. And I am so glad that you are here and will answer our questions. And you people, welcome with Mr. Tyler LeBaron. He is the king.
Thank you.
Okay. Once again, welcome to Munich, Tyler LeBaron. You are the founder, the head and the heart of the Molecular Hydrogen Foundation MHF in the US. A worldwide active foundation that has taken up the cause to spread the quite young knowledge of medicinal uses of hydrogen gas to the world. You are a biochemist and yourself still quite young today in May 2017 on the 29th. You are 29 years old and are most probably the most booked conference talker on this subject. On the advisory council of the MHF are eminent authorities, and you are practically the head coordinator of this worldwide research of this exploding subject. What do you see as the duty of your foundation?
So yeah, I'm the founder of the Molecular Hydrogen Foundation, which is a science-based nonprofit, and we're really focused on advancing the research, the awareness, and the education of hydrogen as a therapeutic medical gas. So we don't sell any products or make recommendations or endorsements. We just really want to focus on advancing this research and bringing the awareness of what hydrogen is, because it's still very much in its infancy, the hydrogen research. Really, the research started in about 2007 when an article was published in Nature Medicine that showed hydrogen could have therapeutic benefits. But the research has grown since then exponentially. I mean, there's still only maybe around 1,000 publications or so of molecular hydrogen, which, although one could consider is quite a bit, and it is growing exponentially, but in the field of academia, it's still a very small amount of research, and so we really need to understand this molecular hydrogen more, and it's a very fascinating area. And so with MHF, we're hoping to just bring forth that awareness, get the education out there to people, because one thing we see, and this is long before it was even known that hydrogen was very therapeutic, was hydrogen is safe. We produce it by our intestinal flora, and we're exposed to it all the time, something very natural. They've used it in deep sea diving back in the 1940s to prevent decompression sickness, or the bends, because hydrogen has such a fast rate of diffusivity, it goes out of the body very quickly, so it's not going to have that toxic buildup, for example. And the human study they've done at literally millions of times higher concentrations than what we need for therapeutic use have really shown the high safety profile of hydrogen. So because we see that it's safe, and we see the various studies out there, clinical studies and animal studies and cell studies, tissue studies, and different animals have been used, not just your rats and mice, but pigs and dogs and monkeys and some different animal models. We're starting to see that actually hydrogen may really have some remarkable benefits, but we need to understand exactly how that works and why, and for the dosing, and there's so much to understand. But because it's safe, it's certainly something we need more research on, and perhaps this could benefit a lot of people.
With regard to the pedagogic duties of your foundation, maybe we should first put in order for some of our audience all the basic principles of hydrogen, so that we not only know what we are talking about, but in front of everyone about what we are not talking about. A bit of chaos surrounds the different forms of hydrogen. Most know it as a component of water, H2O. But then Quite a few definitions are floating around, like H, H+, H-, hydroxide, protons, hydrogen ions, active hydrogen, hydrogen radical, hydrogen superoxide, oxyhydrogen gas, and much more. What is the issue for your foundation with such interesting molecular hydrogen?
One of the main questions I often get is, well, what is hydrogen in general? Like, water is H2O, so isn't that already hydrogen? Or if you add hydrogen to the water, well, isn't that like you're going to have H3O or H3O plus, which is the hydronium, which is acid? Or is this acid water, or is it alkaline water because pH stands for potential hydrogen, so the more hydrogen, the higher the pH, or all these things. So let me go through some of these things. But first, let me explain what we're talking about with molecular hydrogen is simply hydrogen gas. That's what people want to use for the alternative energy source. It's simply two hydrogen atoms that are combined together to form a hydrogen molecule. So it's just di means two, so it's diatomic hydrogen. That's hydrogen gas. It's not bound to anything else. It's free, it's available, it's not bound to anything else.
So is medicinally used hydrogen in hydrogen water by inhalation, injection or infusion quite the same thing as what I use to tank up a hydrogen car with fuel cells if I want to drive it?
Yeah, so the exact same hydrogen gas that you are putting into your water, whether bubbling in or whatever, that's the same hydrogen gas that people use to put into their car or other things for a fuel source. And it's a great fuel source. It's 3 times more energy dense than gasoline by mass. So, but we're also seeing it's great for the human body. And so it's a very exciting area. It's the molecule of the century, if you will, for both of these aspects. But when you add a hydrogen gas to the water, you're not hydrogenating the water, or in other words, you're not making the hydrogen bond to water molecules. It doesn't do that. It just dissolves into the water. Like if you add salt to the water, you get water with salt in it, water with sodium chloride. The sodium ions don't actually covalently bond or something to the water molecule. I mean, it's just dissolved. So same with the hydrogen gas. So you don't form like H4O or H3O or these different structures of the water or something. Is simply water that has hydrogen gas in it, and once you have a saturated solution of the hydrogen gas in the water, you should drink it quite soon, or else the gas will simply escape out of the water. So there are different forms of hydrogen, and maybe we could talk about those briefly. When you look at the water molecule, many people know it looks kind of like Mickey Mouse, right? You have the big oxygen and the hydrogens that are attached to it. But notice the hydrogens are attached to the oxygen. So those hydrogens are not available. I mean, most compounds have hydrogen in them. And let's look at sugar, for example, glucose, which has the chemical formula of C6, C is carbon, so C6, 6 carbons, and 6 oxygens, and 12 hydrogens. So glucose has 12 hydrogens in it. Water has 2 hydrogens in it. But yet, those are completely different because those hydrogens are bound to the glucose molecule, or bound to the water molecule. So you have a totally different structure. And remember, the structure of the molecule always dictates its function. So when we have hydrogen gas, there's 2 hydrogen atoms that are all by themselves, and that's the smallest gas. It can diffuse through cell membranes very quickly, and it can go everywhere very quickly. It's the smallest molecule there is. That's the molecular hydrogen. It's not bound to anything else. The other hydrogens, often people say hydrogen, they also refer to the hydrogen ion, meaning like the H+, which is a positively charged hydrogen atom, has no electron, just has simply 1 proton, and this hydrogen ion is actually what makes the water acidic. So if you have an acid by definition is something that can donate an H+ ion. So if you have a molecule that is an acid, then you have the molecule, and if this is the hydrogen ion, it can donate the hydrogen ion into the water, and that'll make it acidic. And because acid and base, that's about the pH scale. And pH, we can briefly talk about. The P in pH means potential or power, but this is a mathematical expression. The power is like the power of 10, and in this case it's an exponent, which is, well, specifically it's the negative logarithm, which is the inverse exponent. So the P in pH really means the negative logarithm, and the H is the H plus. And so really it's the negative logarithm of the H plus concentration. And that's what pH really means. And so when we hear pH, we're talking about the H plus ions. So by having H plus ions in the water, then the more H plus ions we have, then we're going to have the more acidic pH, a lower pH, because the negative log of a bigger number is going to be smaller. So that's why H plus is specific to the pH in making something acidic.
Tyler, the whole universe is made of mainly hydrogen. One can speak more of an abundance than a scarcity. There is an enormous amount of it. Why is it still good for us, and why is it useful for our health if we supply ourselves with hydrogen?
So although the universe is full of hydrogen, and hydrogen is the most abundant of all the elements that there are, the atmosphere is still very low, about 0.00055% hydrogen. So when we inhale additional hydrogen gas, or maybe take the hydrogen gas and dissolve it into water and then drink it, what we see is there's still therapeutic effects from that. And this is a very new area in the biomedical research, is that this small amount of additional hydrogen gas has some benefits. Some of those benefits are, for example, reducing oxidative stress, or reducing inflammation, or helping with the cognitive decline. They have studies on Parkinson's disease, arthritis. All of these, they'll have a basis in oxidative stress and with inflammation. So this is why we're now seeing that, yes, maybe having some more hydrogen gas, molecular hydrogen, in our bodies can be beneficial, but the research still is very much in its infancy. We need to understand better which disease models or which people hydrogen is going to be the most effective for. But the preliminary data and some of the clinical studies that have been done so far is very impressive, very remarkable, and we hope that more research will be done so we can understand the true significance of hydrogen therapy.
Oh well, there is so much hydrogen in the universe. Yet in our atmosphere on the Earth, there is less than 1% of it. But where does this tiny amount of this earthly scarce good come from? Hydrogen gas escapes at high speed into the universe. Where is it reproduced? And what meaning does it actually have naturally in our habitat?
Yeah, it's a very interesting question. If we look back at the beginning of time, the Earth was more of a reducing atmosphere. The concentration of hydrogen at the time was a lot higher, and a lot of the hydrogen is produced originally actually from actually some of it was even trapped in the various rocks and things at the very beginning, and there's actually some research suggesting that's where a lot of the waters came from, is with hydrogen gas reacting with oxygen to form water. But also we have, like in the deep sea hydrothermal vents in places where there's reactions taking place with basalt catalyzed reactions, or just metals, iron, or different metals that can donate its electrons and react with the water, and that produces hydrogen gas. And that hydrogen gas in turn is what acted as an energy source for the first organisms, the archaea, the bacteria, and it could basically use the hydrogen gas as an energy source to extract the electrons, and thus was the genesis of life. And as time continued, of course, the atmosphere changed, and hydrogen gas is the lightest molecule of all the gases and has the highest rate of diffusivity, so it escapes the atmosphere very easily, very quickly. But it's still being constantly generated by water or by bacteria. Even in our bodies, for example, we have developed a symbiotic relationship with bacteria on our skin and in our intestines and all over our body. But we see the intestinal microflora can metabolize the non-digestible carbohydrates, and some of that bacteria will actually produce hydrogen gas. So we end up always having basal levels of hydrogen gas in our blood and in our breath pretty much all the time. So it is interesting that we've had this relationship with hydrogen really from the very beginning of time. Hydrogen is really what was involved in even the evolution of your prokaryotes to your eukaryotes, with the hydrogenases, hydrogysomes, and different things in the early days. We have that evolution taking place.
Well, we allow our intestinal bacteria to produce hydrogen and we constantly breath it out. Why is it healthy to inhale it or to incorporate it into us by drinking it?
Yeah, so often people do wonder why we have to ingest more hydrogen if we're already getting hydrogen from our bacteria in our intestines. And it is one of the enigmas, if you will, of hydrogen therapy. The bacteria in our intestines can produce a substantial amount of molecular hydrogen, but what we see though in animal studies and human studies is by taking small amounts more of molecular hydrogen, either where it's dissolved in water or simply through inhalation with a cannula or a gas mask, for example, still exerts therapeutic, protective health benefits. There's a couple reasons why that probably is. One of them is a concentration issue. Even though we get some hydrogen gas from the bacteria and quite a bit of amount of it, we can still get fairly high concentrations by inhaling hydrogen gas when it goes into the bloodstream, gets circulated through, and we get to that concentration to reach the minimal effective dose, which we're still not quite sure what it is. It could be 20 micromolars, for example, at the cellular level. The other thing though is it's about maybe a intermittent type exposure. What we see a lot in pharmacology in general is sometimes you can have a signal that's constantly present and you have an attenuation or habituation of that signal, if you will, a desensitization that occurs. And perhaps that same thing is happening with molecular hydrogen, that when you have a constant exposure, although you have some benefits that are occurring, maybe a continuous scavenging of the hydroxyl radical because it's present, some of the more important effects, such as the cell modulating activity of hydrogen that gives it more of this anti-inflammatory effects or altering protein phosphorylations or gene expressions, this seems to be require more of an intermittent or pulse type effect, a tangent, if you will. And so by taking inhalation of hydrogen at a higher concentration or drinking hydrogen-rich water can give you that intermittent concentration to cause those transient changes. For example, there was an article in 2012 that was published with using a Parkinson's disease model, and they showed that a continuous hydrogen exposure by inhaling hydrogen, about 2%, 24/7, it had no effect on Parkinson's disease. Similarly, when they gave the non-digestible carbohydrate lactulose, which was metabolized by the intestinal flora to produce high amounts of hydrogen gas, that also didn't have any effect. But when they gave inhalation of hydrogen gas intermittently, I think it's about 15 minutes every hour, that did have statistically significant benefits. But interestingly though, in this model that was used, it was still not near as effective as simply drinking hydrogen-rich water. So what we learned from this is this intermittent type exposure is very important. It goes back to what I was talking about the desensitization or the habituation of this signal that is important for the cell modulated activity of hydrogen gas, which is similar with all gaseous or signaling molecules in general. The secondly is the route of administration may be different, because when you alter pharmacokinetics, you alter pharmacodynamics. In other words, when we're taking something inhalation versus taking something orally, you are getting the hydrogen differently. When you drink it, you're going to go through the stomach and into the intestines and onto the blood, versus when you inhale it, it goes directly to the lungs and into the bloodstream. Well, there was an article published in Nature, or Nature Publishing Journal, but out of Kyushu University, Dr. Noda found that the drinking of hydrogen-rich water could actually enact a neuroprotective gastric ghrelin secretion. And ghrelin is very neuroprotective, it has some anti-inflammatory benefits and many others, but the drinking of hydrogen-rich water could induce that secretion of ghrelin. And maybe you don't get as much of that ghrelin levels when you inhale the gas. And so by this different route of administration and by this intermittent exposure, we're starting to understand better why the different effects of hydrogen in different diseases.
I would like to understand more about the solubility of hydrogen in water, about that which we can then drink as hydrogen water. With a salt crystal, one can see how water slowly dissolves it. It is divided into its two ions, sodium and chloride. Yet, hydrogen gas is not a salt. It is a non-polar element, so not soluble as a hydrogen bond, like a grain of salt. Is this not a different type of solubility? Somehow it seems to me that hydrogen doesn't feel so good in water, instead wants to rid itself from it, because basically it is hydrophobic.
Yeah, it's a great question. That's the number one question that I get is, what about the solubility of hydrogen? It's not even soluble in water, so how can you even have hydrogen-rich water in the first place? And even if you get any in there, it's just going to be out immediately because it's just not soluble. And solubility is a subjective term. I mean, everything is slightly soluble in water, even if you just get one atom that gets solvated by water or something, right? But the saturation of hydrogen at SATP, or standard ambient temperature and pressure, is considered to be about 0.8 millimolar, or about 1.6 ppm, which is equivalent to 1.6 milligrams per liter. So if you have 1 liter of water and you're at 100% atmospheric conditions of hydrogen gas at sea level, then you could get about 1.6 milligrams of hydrogen in a liter of water. Now, first off, when someone hears, okay, so there's only 1.6 milligrams of hydrogen in that liter of water, that's not very much, because I take 100 milligrams of vitamin C. Well, what we're forgetting here is that vitamin C weighs a lot more than hydrogen gas. Vitamin C is about 176 grams per mole. So if you have 1 mole, think of a mole like a dozen, right? A mole is a set number. So if you have 1 mole of vitamin C molecules, that weighs about 176 grams. If you have 1 mole of hydrogen gas molecules, it only weighs 2 grams. So the masses are very different. So actually, if you compared the moles to moles, or molecules to molecules of hydrogen gas and vitamin C, you would actually see that there are actually more molecules of hydrogen in a liter of water, saturated with water, the 1.6 ppm, than there are molecules of vitamin C by taking 100 milligrams of vitamin C. There are more molecules of hydrogen. So in this case, it actually is a sufficient dose. But more importantly than that is the fact that when we do the actual scientific studies in animals and in humans, we see that that concentration is effective. Even more so, we see that if we take 1.6 milligrams of water orally of hydrogen, then that's going to be diluted by another 40 liters of water in our human body, and then you're going to be down to a very low concentration, say 10, 20 micromolar concentration. So we can do a cell study that uses that same concentration, and we still see an effect. So the concentration of hydrogen that gets into water can be enough, but we do have to drink the hydrogen-rich water as soon after it's prepared, because it is a gas. It doesn't combine with the water. It's not highly soluble. It is very light. It wants to go right up to the atmosphere very quickly. And so if you can consider it really like carbonated beverages. If you have carbonated water, for example, that's CO2 gas that dissolves into the water. Well, if you leave it out forever, eventually it's going to go flat, and now CO2 is going to go out. Well, same with the hydrogen gas. You put the hydrogen gas in there, it'll eventually go out. It's not going to go out immediately. It's going to take some time. So maybe if you drink it within a half an hour, you're going to get most of the hydrogen gas. Depending on the surface area and how much disturbance there is and the temperature and all these things in the water. Just if you have like a bottle of soda, if you're shaking it around, it's going to go flat a lot quicker. But the half-life of hydrogen is about 2 hours. So if you start with, say, 1.6 ppm, and in 2 hours you come back and test it, you'll be closer to about 0.8 ppm. So if you drink it within a half an hour or so.
So if that is only 1.6 milligram per liter, or rather 1.6 ppm, how can some people claim that they can produce water with a much higher hydrogen content?
Yeah, another question I often get is, because we say that 1.6 ppm is the saturation of hydrogen, so we can't get any more than that, how can you possibly have products that have a higher concentration, 2.6 ppm, 3 ppm, 5 ppm? How is this even possible? Is it possible? Is this just marketing hype? Well, sometimes it is just marketing hype, and they have no idea what the concentration really is. They're just putting a number out there. But you can get higher than 1.6 ppm. The 1.6 ppm is simply the concentration at equilibrium at SATP, standard ambient temperature and pressure. So if you simply increase the pressure, then you can go to a higher concentration. And so if you, and remember, when we talk about the pressure, we're talking about partial pressure of just hydrogen gas, not total pressure. So, for example, if you're at sea level and the pressure is 1 atm, well, that's 1 atm of total pressure. So you have 21% oxygen, 78% nitrogen, and then the rest of these other gases. So that's a partial pressure, so not a total atmosphere, but just partial pressure. So when we have 100% of just hydrogen gas at 1 atm, then the concentration, if you wait long enough, will reach an equilibrium of 1.6 ppm. But like I said, if you pressurize a bottle or do something to increase that pressure higher, then the equilibrium now changes, and the new saturation point is maybe 3 ppm or 5 ppm. And you can just keep on going up with more and more pressure and get higher and higher concentrations. And of course it gets more and more difficult to go up higher and higher in pressure, and the higher the concentration you have, the gas will start to dissipate out a lot quicker. And so you can have 3 and 4 and 5 ppm, and some of the research publications actually use that concentration.
Very well. If people, for example, buy hydrogen water in a special drinking bag, or get themselves an electrolysis device which can work with higher pressure, how are they able to control if then 2 or 3 or even more ppm are contained in the water? In videos from suppliers, you often see a measuring device of the Japanese firm Trustflex. It is able to show a maximum of 2 ppm, and with that one knows that such a measuring method is not possible with all types of water. Now, how do you measure independently of the water type, and how do you measure the values over 2 ppm or even 5 or 10 ppm? All that is offered. For that, is it not best to use the H2 blue test drops, which can determine the hydrogen content with titration? What are the differences between the electrical and the chemical measuring methods?
So measuring the concentration of molecular hydrogen is very important. We have to do that in the research so we know what the dose of hydrogen that the animals or the humans are getting, or what the concentration is in the cell, culture media, or in the blood. So it's critical to measure hydrogen. It's also important for people to know how much hydrogen they're actually getting when they buy products from various companies. But the measurement of hydrogen is quite difficult because the meters and different things out there, they work based upon typically on ions type things, and hydrogen is a gas. It's small, it's a neutral molecule, it's not an ion. Most things are like an ion selective electrode. So for example, pH meter, that measures the H plus ion, so it's an ion selective electrode. Or there's nitrate meters, or different meters, or fluoride meters, or things that measure just that ion. But because hydrogen gas is a neutral molecule, it's not an ion and it's nonpolar, it makes it very difficult. Then you have other things like oxygen. Well, oxygen is also a neutral molecule, it's a gas, but yet we have meters for that. But that's because oxygen has a different property with its electron, the way the electrons are in the outer shell, that makes it paramagnetic. And so we can use that property of hydrogen as being paramagnetic to also measure hydrogen. But also measure oxygen. But hydrogen is diamagnetic, and that also makes it more difficult to measure. So typically to measure hydrogen, you have to use a specific gas chromatography. And then it gets more complicated because you have to have a specific column to measure that molecule because it's so small. And most columns at the universities of things that have a gas chromatography, they can't actually measure for hydrogen either. So it becomes rather difficult. There are meters, or some meters that are claimed, well, you can measure the hydrogen. Most of those meters use basically a volts type meter in order to measure, or well, it's not really measuring, it's really correlating a potential that they're given to what the likelihood of the concentration of hydrogen is. But it's not selective to hydrogen, and they're often pH sensitive, and they're often can be wrong because of the way they're calibrated. There's no actual standard. So the real types of meters that we use in research, for example, you actually have to prepare a samples with a known amount of concentration, so you can make a standard calibration curve. So you have this amount, this amount, you have that calibration curve, and then you can use that and measure your unknown, and you can compare that to your calibration curve, and then we can calculate what the concentration is. That's the standard way. It's a little more difficult and very expensive for most people to do. Then another method that's very easy to use, it's not as accurate, and it's not as precise in terms of being able to measure to very small concentrations like 0.001 ppm or something, like if you're measuring in the blood. But there is the simple redox titration reagents that use a methylene blue with colloidal platinum as a catalyst that's able to make that reaction happen. But it's very simple. You just pour the water into 6 milliliters of pour the hydrogen water into 6 milliliters into the beaker, and then you add the reagent in there, and the hydrogen reacts with the reagent, and it converts the methylene blue from blue to clear. And you can add another drop, and the more you add, the more hydrogen molecules are used, until all the hydrogen molecules are used up, and the reagent turns blue and it stays blue in this case, and that is considered the titration endpoint. And now you can simply calculate what the concentration is, because you know how many drops you added to the water. So that's probably the simplest or easiest method at this point for people to measure the concentration of hydrogen in the various products, or to make sure that what they have is going to be therapeutic.
Good. Now we know the most important things for measuring the control of dissolved hydrogen. Next, we should find out how much of the good stuff we should drink, and also at which concentration. So, for example, is it better to drink more frequently during the day a lower concentration, around 0.5 to 1 ppm, and like that to gradually drink 2 to 3 liters a day? Or would it be better to just drink 1 liter a day with a higher concentration, like 3 ppm?
Another main question I'm often asked is, okay, how much hydrogen do I need to get this therapeutic effect? What is the concentration or the dose that I'm required? Well, we really don't know for sure what the minimal concentration is, or what's going to be the most effective. We can really say what a suitable concentration is, and that's simply based upon the animal, and specifically the human studies, where we've used a certain concentration and it has shown therapeutic benefits. And typically that concentration is around 1 to 1.6 ppm, even higher, even up to close to 5 ppm. But then you have to consider not just the concentration, but the dose of hydrogen that you're getting, because you could drink 3 liters of 1 ppm and that would give you 3 milligrams, or you could drink 1 liter of 3 ppm. Now it also give you 3 milligrams, but the volume of water is different. So if you go through the human studies and you calculate, okay, they drank this much water, the concentration was this, typically the amount of hydrogen they're getting in milligrams per day is about 0.5 milligrams to 3 milligrams and even higher. That's the common range. So getting around the 1.6 milligrams a day, 3 milligrams a day, is probably where you want to be. We are seeing that in some cases it's likely that a higher concentration can be more effective. In other cases it seems to not have any additional benefit. But what we do see, it appears so far, at least from both cell studies and animal studies, that a higher concentration is not less effective than a lower concentration. And that's an important thing, because we already know the hydrogen is rather safe. We can take the higher concentration and feel good that at least we're getting enough that if something were to happen, we should be getting enough that it can happen. So that's kind of where things are at. But because the research is still very much in its infancy, there are about 40 or so clinical studies that are currently registered. 40 has already been done, just human studies and things in general since this inception of hydrogen. But there's another 40 or so that are done. Some of those are just with inhalation, like in the hospitals and things, but many of them are with the drinking of hydrogen-rich water. But we really need more human studies to understand the dosing protocols, and if you're going to get a total of 3 milligrams a day, should you take that 3 milligrams in the morning or at night? Should you take 1 milligram in the morning, 1 in the evening, or 1 at night? Or, what about if you have this disease, maybe we should do it this way, maybe we should do it this way. These are viable questions, and there is some suggestive reasonings about that doing one way or the other may have a different effect, because again, you're changing the pharmacokinetics, and when you do that, you change the pharmacodynamics, if you will. And the concentration that actually gets to the cellular level is going to be higher.
Well, that is the field of therapy. There I can look up the disease in the individual studies and see which dose was successful. And it is important to note the following statement: more hydrogen is not harmful. There are, according to therapeutic goals, only low limits and no maximum limit. I don't need to be ill in order to be enthusiastic about drinking hydrogen water. It also tastes good. And maybe I just want to stay healthier for longer. Or drinking this water should support me in completing a fitness program. In short, wellness and fitness people, even competitive athletes, always ask me how much they should drink and what concentration they need. Does it help with muscle development? And the most pressing question seems to be, can one lose weight by drinking this hydrogen water? Or actually not? After all, plants grow faster if you water them with this water. Even animal breeders discuss the use of it and apply it because there is proof that pigs or chicken gain weight faster from it. Producers advertise the most varied arguments and advertising statements of all that. What is correct and what is marketing drivel?
Another question I often get is about the effects of hydrogen water on weight. We have some people who they drink hydrogen water and they're saying, hey, I'm able to gain weight finally. You have other people that drink hydrogen water and they say, hey, I'm able to lose weight finally. You have other people who drink hydrogen water and say, my weight stays the same. So which is it? Is hydrogen water going to help you lose weight? Is it going to help you gain weight? Is it going to do nothing for you? Or is it just going to do whatever you want it to do? I don't know. We need to have more human studies to understand this area better. Now, we can talk about some data we have to suggest that it can maybe do one thing or a different thing. For example, there was a study in a Nature Publishing group in the Journal of Obesity that showed that hydrogen-rich water can, it basically induces FGF21, which is fibroblast growth factor 21, which helps to stimulate energy metabolism, specifically the expenditure of fatty acids and different things. And if you have an increased metabolism, an increased metabolic rate, then you're going to burn more calories. And in fact, in the study, they also had one group of the rats, or maybe it was mice, I think it was mice, and they were on caloric restriction, and the other group was not, but they drank hydrogen-rich water. But they found that the drinking hydrogen-rich water had a similar effect as at about a 20% caloric restriction. It was on a high-fat diet. Then they also did a combined where they showed that hydrogen water and caloric restriction had an even greater effect. So this study suggests that actually, yes, hydrogen may be able to help with the weight loss because it's able to activate this FGF21, induce this energy expenditure, improve the metabolism. There are other studies on the hydrogen's effect on the mitochondria and many different aspects where, yes, it starts to make sense. Okay, maybe hydrogen can help with this weight loss, this fat loss. Then on the other side, what about these people who say they can finally gain weight? Well, there are some things to consider in that realm as well. We talked about earlier how hydrogen-rich water can actually induce neuroprotective gastric ghrelin secretion. So ghrelin has some anti-inflammatory properties. It's a hormone. It's very beneficial. In fact, one of the reasons why fasting or intermittent fasting may be good for you is because you have higher levels of this ghrelin, and ghrelin mediates some of the benefits of fasting. And interestingly, like I said, hydrogen-rich water can also increase ghrelin levels. Well, ghrelin, this hormone, is actually the hormone that makes you feel hungry. And so for some people, maybe they're getting higher ghrelin levels and so they're eating more. And because they're eating more, they're finally able to gain more weight that they've been wanting to. Additionally, ghrelin, the hormone itself, just GHRELIN, it stands for growth hormone releasing hormone. That's what it is. And growth hormone, of course, is an anabolic hormone. And it helps to build muscle mass, helps to conserve muscle mass and different things, lots of benefits. So maybe hydrogen increases growth hormone a little bit. by the ghrelin secretion, and then growth hormone in turn can help to build the more muscle. So for the athletes in different areas, you're able to help gain weight. Maybe you're eating more, maybe the growth hormone is going on. And then you have the other group where they don't really have any effect on their weight loss, and maybe that's because they didn't need any. Or maybe they do want, but it's not having that effect. Everybody's different, so maybe some people it won't have such a dramatic weight loss effect. It's been reported anecdotally, or even in some of the studies, or vice versa, with this other idea of gaining weight.
Here an interposed question from Mr. Yasin. He would like to know how you personally are holding up with fasting. Do you recommend it? And if so, when? And for how long should one fast, or rather adhere to meal breaks?
Another thing that I'm asked about is fasting in general, because I've talked about how hydrogen-rich water can induce gastric ghrelin secretion, and fasting also increases ghrelin levels, and so they're mediated by this same second messenger molecule, ghrelin, some of those benefits. So do I fast? Is fasting good for you? Is it good to do it in conjunction with hydrogen? Probably. I fast between meals all the time. But fasting is certainly good for you. We see studies in animals. We do need to see some more studies in humans to see the real benefits of the intermittent fasting and different things that are going on. Caloric restriction in general is a good thing, especially if people are suffering from obesity or different things. The caloric restriction can be very beneficial. We see different changes in many different hormones and molecules and insulin and IGF-1 and different things that can be beneficial in helping DNA repair. Can hydrogen potentiate the actions of fasting? I wouldn't doubt it. We see hydrogen can induce gastric ghrelin secretion, it can induce FGF21, it can stimulate other DNA repair mechanisms, which also fasting does. In fact, hydrogen seems to activate some of the same metabolic pathways and transcription factors and things that fasting does. So maybe there would be an additive or synergistic effect, or maybe the fasting's effect would be so great that you wouldn't see any of the effects of hydrogen. We just don't know. We do see one of the studies that there was at least an additive, potentially synergistic effect with the caloric restriction and the drinking of hydrogen-rich water, so it's probably a good idea. But then we have the question, okay, so when do we take the hydrogen? So we take it with the meal? Should we take it while we're fasted? What's the best way? Again, we really don't know. Maybe it's best to take it with the meal, because on this hand, if you take it with the meal, then it's going to help the body with the metabolism or something, and it's going to be able to, some of the hydrogen has been shown to actually be stored a little bit in the glycogen in the liver, and as the glycogen is burnt and the more the hydrogen that gets accumulated in there releases out, and so it just stays in the body for a little bit longer, and so maybe that's a good way. But then maybe it's better to take it more on an empty stomach, because that way the body's fresh, the hydrogen is able to just go right into the body, and there's no other molecules and foodstuffs that's in the body that's changing things or something. So maybe it's better to do more on a fasted. So I don't know, but for me, I guess I prefer to take my hydrogen in the morning before I eat, or just different times than with a meal, just because I typically don't drink a lot of water with my meals anyways, but drinking hydrogen-rich water with the meal or fasted state, we really don't know what's going to be the most effective, if there is an effective way, but it's possible that taking in a fasted state, due to this one study and some other mechanisms of action, could make it a little bit more effective.
And when to eat then best, or when to fast?
And then people are also asking me, okay, so when should I eat? When should I fast? Well, if really there's a lot of research, and it's equivocal. Some of it's rather contradictory. You don't know which one it is, and I'm not an expert in the fasting field, even though I fast, like I said, between meals. But there is an article I remember reading a bit ago where they found that they had two groups, both on caloric restriction, but one of them ate like 70% of the calories in the morning, maybe 20% at lunch and 10% at dinner, and the other group just the opposite, with 10% in the morning, 20% at lunch, and the 70% at dinner. And at the end of the study, they found that they both lost the same amount of weight. But what's interesting about the study was that the group that had the larger dinner primarily lost fat, whereas the other group lost a lot more muscle. And some of the reasonings that was suggested from this smaller human study was that maybe when we sleep, that's a time where the body repairs itself. You have increases in growth hormone. We need to have enzymes. The body has to build enzymes, which uses the building block of amino acids to make those proteins. So if you have no substrate or no food in your blood or in your stomach or something, then the body's got to get those amino acids from somewhere, so it can break down the muscles to get those amino acids to make the proteins and the enzymes that it needs so it can do its repair mechanisms and things. So maybe going to bed in a fasted state is not the best idea. And in the morning, you're already really busy anyway. So even from a psychological perspective, for those who are trying to lose weight and do a caloric restriction, it makes sense to me that eating a small or even skipping breakfast could be the easiest thing, because you're already so busy trying to rush out the door and get to work and different things. And then the lunch is just small and mild, and then in the evening you have a good, nutritious, healthy meal. And that's also a very social time where you're with your family, you're with friends, and you can go ahead and eat the majority of your calories at that time, and then you go to sleep. And you're fasting, if you will, until the next time, but you're not starved. You have actually substrate for your body to work off of. Again, more research needs to be done on the ideas of fasting and intermittent fasting, what's going to work the best, and all these different things. It is a very interesting area, and it does have some carryover to this hydrogen therapy.
Mr. Akün has a very interesting follow-up question, which is to be expected of a water that is saturated with the energy-rich hydrogen gas. And so far as I know, it has so far not been answered. The hydrogen in water, which signifies an excess of electrons, which can be measured as a negative ORP. Could it be a type of nourishment in the end? And due to that, could one renounce the usual ways of staving off hunger with the usual calorie-rich foods?
So with the fasting and the hydrogen, also people say, hey, when I drink hydrogen water, I feel so much more energy, like it's a food to me, where I just have this energy and I don't have to eat anymore. Well, potentially maybe that's placebo effect. We do see hydrogen can help increase and stimulate the mitochondria. It stimulates energy expenditure, so maybe there's more ATP equivalents or different energy there that's available for use and helping to lower inflammation or oxidative stress, and so you just feel more alert and more clear. So those are all possible, but hydrogen itself it's not considered a nutrient, or it's not actually metabolized by the body and used as an energy substrate by NAD plus to NADH, or in the electron transport chain of the mitochondria, actually used to make ATP. It's not used directly, but we do see that it can actually increase the mitochondrial membrane potential. It can increase ATP production, specifically if the mitochondria is compromised for one reason or the other. So it is possible that the drinking of hydrogen water may give you some sort of satiety, just because it's able to give some more mental clarity and things. But it could also be just because you're drinking water, and water induces gastric distension, making your stomach feel full, and gastric distension is one of the most potent signals for satiety. And so simply drinking more water can help you not feel hungry as well.
I guess one has to have patience until science, in the light of new possibilities which offers energy-rich hydrogen water. The term nourishment can maybe one day be redefined or raised to a higher level of abstraction. Until now, water counts as a foodstuff. In fact, the most important, yet not as a food, because it is seen as calorie-free. The last word has not been spoken on this matter. Obviously, one wants to assume that released electrons could mean something like an energy transfer. On the other hand, does molecular hydrogen only give off its electrons under adverse circumstances, namely when it encounters the very aggressive hydroxyl radical? This can maybe not be understood or seen as triggered energy metabolism from food. Or can it? This difficult question, which delves into the fundamental and philosophical nourishment definition, cannot currently be finally answered. Instead, let's shed some light onto what we already know about hydrogen water, which we take in by, for example, drinking. How long does it take until the gas reaches individual organs and its effect can unfold?
Another question I'm often given is, what about the pharmacokinetics of hydrogen? In other words, when I take my hydrogen water, how long does it take for the hydrogen to actually get inside of my body, and how long does it stay there for? Well, what we've seen in some of the human studies is people can drink hydrogen water, and then we see increases in breath hydrogen, because what happens is you drink the hydrogen water, it goes into the stomach, goes into the intestines, goes through like the portal veins to the liver, and then into the venous system of the blood, and then directly to the heart, and then to the lungs, and you exhale most of this hydrogen gas out. And so you can measure increases in breath hydrogen, which also clearly shows that hydrogen does make it through the intestinal wall, the submucosal, into the bloodstream. And typically, depending on the dose of hydrogen you're getting, you reach the peak level within 5 to 15 minutes or so. So it goes through quite quickly, and having such a high rate of diffusivity, being so small, it's able to penetrate through the cell membranes, and it's able to, it's very ubiquitous and pervasive in that it can go out through everything quite easily. And probably in about an hour or so, again, depending on the dose, the bigger the dose or the more you drink, the longer it's going to last, or the longer it'll take to get to that peak level. But within an hour or so, it's typically back down to basal level. So if you measure breath hydrogen in your breath, you probably have maybe 5 ppm of in the air. And then if you drink the hydrogen water, say 500 milliliters at 1.6 ppm, and it jumps up to 80 ppm or 115 ppm or something like in this range, then it goes back down, and within an hour you're back to normal, 4 or 5 ppm of breath hydrogen in the air. So that's basically the pharmacokinetics of the hydrogen from drinking hydrogen-rich water. Then of course there's inhalation. And of course that's very, very rapid. If you inhale the hydrogen gas, it does depend on what percentage. Many of the studies, they use a percentage below 4%, because at a 4.6% that's when it's flammable, and so if there's a spark or if there's some sort of ignition source, that could light the gas on fire, and that would not be so good. So a lot of the studies are below that time, and the hydrogen is going to just follow the blood flow, and it can go throughout the body quite quickly, and it does reach muscles in the brain and different things, and reaches an equilibrium depending on the concentration that you're continuously inhaling within maybe a half an hour or so, and then once you stop inhalation, again within about an hour, it typically goes back down to baseline, again depending on the volume you're inhaling. There are some studies that actually use a 66% hydrogen concentration, 33% oxygen, and those ones of course will stay in the blood a lot longer. And then the question is, well, which one's better? To inhale the greater or to inhale the less? Well, again, we don't know. We need to see more human studies in order to figure out which one's going to be better. Maybe, because we do know that it is a difference if you inhale, let's say, 0.1% hydrogen gas for all the time, say for 24 hours. That may not ever be effective or therapeutic because it never actually reaches the concentration at the cellular level high enough to exert this therapeutic protective effect. So we typically see in animal studies at least, and then extrapolate to the cell culture, that the concentration needs to be closer to 1% or higher. Typically 2 to 3% or so is, or a lot of the studies are. The big study in Japan, for example, is the government recently approved hydrogen inhalation as a medical procedure for post-cardiac arrest patients. They're using about 2 to 3% hydrogen concentration, so it's below the flammability level. And point is we know we have to get to a certain cellular concentration in order for the hydrogen to be effective. And then the question is, okay, so now say that you are to that therapeutic level. Now does it matter if I'm inhaling the 3% hydrogen or 66% hydrogen? Well, then we need to consider, okay, what disease are we talking about? Does this disease have a dose-dependent effect, or does it not? And then what kind of a tangent or impulse type intermittent exposure does this need in order to optimize the effects? And we just don't know at this point. There's more anecdotal reports of what we should do than there are scientific data and evidence than suggesting what we need to do. So we're still in the research process of this. So because we talked about the pharmacokinetics and that when we drink the hydrogen-rich water, that it reaches a peak plasma and breath level within 5 to 15 minutes and then goes back to baseline within an hour, then people will say, oh, so maybe I should be drinking hydrogen-rich water every hour so that we go up and then we go down, then we go up and then we go down. Maybe that makes sense, but we don't know, and there could be some other things to consider. Maybe it's actually better to let it go up really high like that and then go back down, and then we wait and give it no signal, nothing there for an extended period of time, and then we hit the cell again with a higher concentration after that, because you have this metabotropic effect, the changes in gene expression, different things. All these take time to change back to how it was or to make the changes, and so we don't know if it's best to just drink it on the hour or maybe just have it once a day or have it 3 times a day. And then again, like we said, should we have it with the food or without the food? How does that all make? We don't know. What we're seeing in the animal and human studies is the drinking of hydrogen-rich water is effective, and there's probably not necessarily a wrong way to do it, but there probably is a better way to do it. We just don't know what that better way is at this point.
Back again to the intake of hydrogen after drinking. How much of it enters the bloodstream and how much floods the body directly as a gas, so that everything is penetrated and not dependent on transportation through the blood vessels.
We talked about the pharmacokinetics of the drinking hydrogen-rich water, that it goes through the portal vein into the systemic circulation, through into the venous blood. How much of that hydrogen we exhale it out, and how much actually goes throughout the rest of the body? Well, most of it actually is just simply exhaled out, and 95% of it is exhaled out, or even higher than that. And so the question is, well, then how much actually gets to my tissues, to my muscles, to my knee? How much of that hydrogen molecule actually gets there? Probably a very small amount. And so that suggests that we have other secondary messenger systems that are probably work like ghrelin that we talked about, or parts in the liver. We also have the counter-multiplier effect in the kidney, where even small amounts of hydrogen, but it's passing through the kidneys so often, so that's one of the reasons we're seeing benefits to the kidneys with oxidative stress and kidney function and glomerular filtration rates and different things. so again, we need to see more studies on, you know, what the dosing is and the reasons for why this works better than this works, or if it even does.
So now we know that we know relatively little about how the intake of hydrogen in the body should be dosed. One issue, though, which has been long discussed even before the pharmacological effect of hydrogen gas in water was even known, is that the antioxidant effect of water has a negative redox potential, or ORP. What does the antioxidant effect consist of actually, and what differentiates it from other antioxidants?
I'm often asked the question about hydrogen as an antioxidant, because we already get so many antioxidants that are available in our food and by supplements and everything. Why take hydrogen, just another antioxidant? Well, in reality, I would say that's kind of a misleading. I don't really consider hydrogen as an antioxidant. It is a reductant, has a reducing property by nature because of its hydrogen gas, but it's not a conventional antioxidant in any way, shape, or form. Antioxidant is more of just a marketing term, hurry and get it out there. The Nature Medicine publication in 2007, the title was, hydrogen acts as a therapeutic antioxidant by selectively scavenging cytotoxic oxygen radicals. And that really maybe helped get it a lot of press, a lot of interest, because everyone knows the antioxidant buzzword. But it's much more complicated, elaborate, and amazing story than that. And we should talk about that a little bit more, because really it should not be considered an antioxidant. Really what's going on is, first let's look at the antioxidant property of hydrogen. An antioxidant is a molecule that's able to donate its electrons to an oxidant and neutralize that. So like vitamin C, ascorbic acid, or vitamin E, tocopherol, or other polyphenols are antioxidants because they can lose their electron from what's called a conjugative pi system and be rather stable, lose that electron, donate it to that free radical, and neutralize that free radical so it doesn't wreak havoc in the body, because of course free radicals, they are linked to aging, diseases, and so many other problems because they can just oxidize and damage your DNA and your proteins and cell membranes, and of course that's what makes the apple turn brown or causes the rust. It's all this oxidation, and that can cause problems on the body. So that's what antioxidants are. So how does hydrogen gas compare as an antioxidant to these other antioxidants? Well, if we just look at the molecules first themselves, okay, hydrogen gas is a very small molecule. It's the smallest molecule that there is. And so things that are going to dictate cellular bioavailability is the size of the molecule. In order to scavenge any free radical, it actually has to get to where that free radical is being produced. And most free radicals are produced in near the mitochondria and the various complexes, 1 and 3, and different places. Hydrogen gas actually got to get there, which it can very easily. The antioxidants have to get there, but because hydrogen is so small, it's able to diffuse through the cell membrane into the subcellular compartments of the mitochondria, nucleus, and different areas very easily. Whereas some of these other molecules, they need to go through transporter mechanisms, or maybe because like vitamin C is more hydrophilic, water soluble, it has a difficult time getting in through the cell membrane, or maybe vitamin E, which is more fat soluble, hydrophobic, wants to stay in the cell membrane, so it doesn't want to be in the water space very much. So it makes it a little bit more difficult for those molecules. So just on the physical properties, chemical properties of hydrogen and the other antioxidants, hydrogen is superior because it really can get into the cells very easily, and where it can potentially scavenge these radicals. But does it really scavenge the free radicals? Well, first off, hydrogen, and the Nature Medicine paper said this, is a selective antioxidant. So what is a selective antioxidant? Well, basically we have lots of free radicals, or a better term that includes free radicals is reactive oxygen species. And that includes like hydrogen peroxide, which is not a free radical but is a reactive oxygen species, or ROS. It includes all of these, and these ROS molecules are both bad for you and they're good for you. Kind of like cholesterol. You know, for a long time people were saying, hey, cholesterol is just bad for you, let's get rid of all of it. And they're like, oh wait, there's HDL and there's LDL, and now we're finding there's different patterns of the LDL and the HDL. You know, some of them are better or worse. Same thing with the ROS, the reactive oxygen species. Some reactive oxygen species are good for you, some of them are bad for you. A lot of the cell communication and the way cells work are based upon this redox chemistry, okay, of transferring electrons and free radicals. In fact, the vasodilation, or widening the blood vessels, is caused by a free radical known as nitric oxide, which many of you are familiar with. Nitric oxide is a free radical. It's rather stable. Of course, it's not stable as a free radical, but it's more stable. But it's produced at a specific location, and it reacts with its target, and it causes all of the benefits that nitric oxide does. And of course, if that radical nitric oxide gets too high, then it wreaks a lot of havoc, causing nitroxidative damage, reacts with superoxide radicals to form peroxynitrite, and peroxynitrite is an oxidant that's very damaging, very, very harmful for you. And when our immune system uses reactive oxygen species and to kill the pathogens. So we need these free radicals. Even when we exercise, we produce more free radicals because we're breathing so much more oxygen, so we have more free radical production. And these free radicals are actually what likely mediate the actual benefits of exercise, because these free radicals activate transcription factors that induce like mitochondrial biogenesis, more mitochondria, more energy producing organelles in our cells. So a lot of these benefits are produced by these free radicals. So what dictates if a free radical or a reactive oxygen species is good for you or bad for you? Well, the main thing that dictates that is the reactivity of that free radical. So like I said, nitric oxide is a free radical, but it's not as reactive as, say, another radical, such as the hydroxyl radical, which is just OH neutral, has a lone pair electron. It's very reactive, very cytotoxic or cell damaging. And this hydroxyl radical can be produced when there's an excess amount of other free radicals like superoxide via Fenton reaction, or through the hydrogen peroxide, through various catalysis mechanisms that can produce hydroxyl radicals. This hydroxyl radical is just very damaging. In fact, there's really no known benefit for it, and there's no detoxification enzyme specific for that. So you have radicals like superoxide anion radical. There is a specific enzyme the body produces to handle that free radical called superoxide dismutase, or SOD, or SOD. And you have other things like hydrogen peroxide, which is a oxidant, and you have things like glutathione peroxidase or catalase that can handle those oxidants. But there isn't anything like that for the hydroxyl radical. Hydroxyl radical is just very reactive, and it reacts with everything and anything in its path. Well, hydrogen gas is a very mild, very weak antioxidant, if you will. And it doesn't react with anything. In fact, in order for hydrogen gas to react with anything, something has to react with it very powerfully. And the only radical that is strong enough to do that is the hydroxyl radical. It's so powerful that it can actually react with hydrogen gas, and when it does, it forms water. That's the reaction. So it's kind of a neat story, just like that. It forms water as the byproduct. So hydrogen gas will not, indeed it cannot, react and scavenge all the other radicals and reactive oxygen species, many of which may be very beneficial for our body, that we don't want to scavenge. And so actually that could help explain why some of these clinical and humans large studies using antioxidants have shown that taking high levels of these exogenous antioxidants often have deleterious effects, can be harmful to our health. Maybe because they're scavenging too many of these beneficial molecules, these beneficial reactive oxygen species that we actually need. And it's perturbing or exacerbating this dysregulation of this redox balance. So hydrogen, if it scavenges anything, it's only going to scavenge this hydroxyl radical, and the Nature Medicine paper also mentioned potentially then peroxynitrite molecule, which is very oxidizing as well. But even with that, the benefits of hydrogen cannot really be attributed to the scavenging of hydroxyl radicals. There's too many explanations and reasons and evidence that it doesn't make very much sense that that's where it's doing all the benefits. Really, what we're seeing the benefits of hydrogen is in this cell modulating activity of hydrogen, or where it's acting as more of a gaseous signal modulator like other gaseous molecules. Nitric oxide is a gas, hydrogen sulfide, carbon monoxide. These are well recognized gaseous signaling molecules, and hydrogen has a similar idea where it can do that. And there was an article just published in May of 2017 where it showed that hydrogen could actually has a in the mitochondria, increase in mitochondrial membrane potential, increase in ATP production, but it was doing this because it had a transient increase in the superoxide radical production in the mitochondria. And this radical increased production then activated other transcription factors, including like the NRF2 pathway, which induces as a transcription factor, which induces more antioxidant enzymes like glutathione and superoxide dismutase. So maybe this is one of the mechanisms that hydrogen works, is more of a hormetic, a hormesis mechanism, mitohormetic, which is able to transient increase in ROS production, and that mediates many of the benefits of hydrogen. So if rightly understood, one could consider that hydrogen is good for you because, one, it is a very weak antioxidant. It doesn't scavenge all the good ones. If it scavenges anything, it's only going to scavenge the very bad radicals that cause the most damage. And two, it's kind of like potentially a pro-oxidant, in that it actually can increase very small amounts, not enough to be toxic, just enough to induce transcription factors. It produces just enough oxidant, the superoxide radical, in the mitochondria. We've seen with adding galactose instead of glucose, but we see that it can increase transiently small amounts of ROS, and that in turn mediates a lot of these benefits. So again, if rightly understood, hydrogen is beneficial not because it's a powerful antioxidant, but because it's a very, very weak antioxidant that only goes after the bad guys, and is a small pro-oxidant that works kind of like how exercise does. We increase amount of free radicals just a little bit, and then we get all the benefits after that.
The presence of dissolved hydrogen gas causes a low negative redox potential, which can be measured as ORP. But what is surprising for many people, a low and negative ORP does not yet mean that a lot of hydrogen is dissolved in water. How can this be explained?
So often I'm asked about, what about the ORP meter, or the measurement? ORP standing for oxidation reduction potential, and this using to measure the amount of hydrogen in the water. Well, it doesn't really work that way. It's not specific to hydrogen, and it's not a very accurate method for measuring hydrogen because it's not specific to hydrogen. The ORP, really how it works is what it stands for, is oxidation. Okay, so we have something oxidized species, and reduction, so we have reduced species. Potential, potential means difference. So really it's the difference between an oxidized species and a reduced species, and it's just a ratio of that. It's actually a negative logarithmic ratio of that difference between the oxidized species and the reduced species, and that's based upon the well-known Nernst equation, and this can be calculated, and that's really how it's working with when you add anything to water. So when you have a solution and you measure the ORP of that water, it's going to give you a number, and it could be a positive millivolt number or a negative millivolt number. If it's a positive millivolt number, all that means is that there are more oxidized species, not necessarily oxidizing, but just more oxidized species than there are reduced species. And if it's negative, there are more reduced species than there are oxidized species. So when you get the negative ORP reading, you should first ask yourself, okay, what is responsible for making this negative ORP? Is it good for you or is it bad for you? Because you can add all sorts of things to get a negative ORP. You can add a number of chemicals that are toxic for you, whether trigonolines or dihydropurines or beta-mercaptoethanol or different redox states and metals or different things. They can all give you a very negative number, but if you were to drink it, it could be rather toxic for your body. So just because something has a negative ORP does not in any way, shape, or form mean that it's actually good for you. So the first question is, when you see a negative ORP number, ask yourself, what's making the negative ORP? And now you find out, okay, that's actually bad for you, I don't want it. Or you find, hey, this is good for you, such as maybe it's from vitamin C, maybe some polyphenols from like a tea or something, or maybe it's from hydrogen gas itself, because when you dissolve hydrogen gas into water, it gives a very nice negative ORP. So now you know, okay, the negative ORP is in there not because it's bad for you, because it's good for you. These molecules are good for you. Then the next question to ask yourself is, but is the concentration enough to even be worth my time? Because again, the ORP is not, it's not measuring a concentration, it's a negative logarithm of the ratio of that difference. And so it has nothing about concentration in it, it's just the greater the difference, and then it's negative log, so it's going to make the number even bigger than it really is. So you get that number, whether it's negative 500 millivolts or anything, you still actually have no idea what the concentration of the active ingredients are. So let's say we talk about hydrogen gas. Well, because in this case with just water and hydrogen gas, you have the reduced species, which is hydrogen gas, H2, and you have the oxidized species, which is H+. And you include oxygen and some other, maybe some chlorine in there if it gets in there. These are the oxidized species. But let's focus on the H2 and the H+. Well, H+, that is what pH is, we talked about. The more H+, the more acidic. And the less H+, the more alkaline. And if it's H2 divided by H+, well, if we have alkaline water, we have very little H+ ions, so therefore a numerator divided by a smaller denominator is going to give a larger quotient, and the negative log of that quotient is going to give a more negative number. So you get something that's very large. So the more alkaline the pH is, the more negative the ORP becomes. But notice we didn't change anything in this case with the numerator, with the actual hydrogen concentration. So theoretically, if everything worked out perfectly, then based on the Nernst equation, we could calculate what the pH is, get the H+ concentration, and then do the inverse exponent, and we could figure out the concentration of hydrogen is. But it doesn't work that way. I've tried it. It's just, you have totally different concentrations. And the reason why is because this ORP meter, again, is not specific to just hydrogen. And we're talking about a changes in concentration that is very small compared to what's going on. So, for example, in normal tap water, we have hydrogen gas in the atmosphere, very low amount, 0.0005%, and that hydrogen also gets dissolved into the water, so now you have a concentration of, say, 0.000001 ppm. Now, if you measure then the ORP of just your water, you say you have positive 300 ORP millivolts, positive 300 millivolts, well, and you have that much hydrogen gas in it, 0.00001 ppm. Now, if you increased the concentration of hydrogen 1 million times, right, then you would get 0.1 ppm, about 0.1 ppm. You increased the concentration 1 million times. So because it's logarithmic and the ratio and everything, you're going to see that ORP reading is going to go from, say, positive 300 to negative 500, because you changed that 1 million times. Now let's say you're going to go from 0.1 to 1 ppm. So you changed it 10 times. If you change it just 10 times, you're not really going to see much of a change at all in the ORP. It's still going to be around negative 500 millivolts. So we just don't see very much change at all with increasing the concentration of hydrogen. And that is why, and I've done this many times, you can do it as well, you can actually say, have 2 glasses of water, both of them have an ORP of, say, negative 500 millivolts, but one of them has a hydrogen concentration of 1 ppm, which can be therapeutic. The other concentration is, say, 0.1 ppm, which may or may not be therapeutic. But the ORP is the same. You could actually have it where one is 1 ppm, the other is 0.1 ppm, but the one with 0.1 ppm has an ORP of negative 800 millivolts. Why? Because the one with 1 ppm is a neutral pH, the one with 0.1 ppm could be a pH of 10. And all of a sudden that will show a much higher concentration, because again, pH is also logarithmic. So if you go from a pH 7 to a pH of 10, that's 7, 8, 9, 10, that's 10, 100, 1,000 times less H plus ions. So you have 1,000 times less, smaller of a number on the denominator, and now the numerators they stay the same, but all these things make the changes so it's reflected exponentially, because it is an exponential problem, a logarithm, in that changes. So you cannot use the ORP meter to see which concentration is higher. Now, there can be some benefits of using an ORP meter. In general, fresh fruit and different things, fresh juices should often have a negative ORP reading. And so you could say, hey, if it's fresh, have a negative ORP reading. That's fine. When it comes to the hydrogen, you can't use it at all in any way to see which one has more hydrogen than another. But I will say this, that you cannot, if you have a high concentration of hydrogen, say 1 ppm or greater, you'll always have a rather low negative ORP, say negative 4, negative 500 millivolts or less. So if you have a negative 4, negative 500 millivolts, you know that you have a concentration of hydrogen that's maybe, it could be 0.05 ppm to 10 ppm. It could be all those numbers. But if you have an ORP of, say, negative 10 or positive 100, then you know there is no hydrogen in that glass of water. So really, if it has a negative ORP, there's hydrogen, you just have no idea how much. Sorry, if you have a negative ORP and you know that the chemical species in the water is hydrogen, then you know that there's hydrogen in there. You just don't know how much there is in there. So you have to measure that, and you can use, like I mentioned earlier, the redox titration reagent. So that's very important to remember. The only benefit is if you use the ORP meter, you measure the water that claims to be hydrogen, and you're only getting, negative 50 or a positive number. You don't even need to worry about measuring the hydrogen, because there isn't going to be any suitable concentration.
Some do believe that they do not have to laboriously measure if hydrogen is dissolved in water. They then show, for example, how the water flows out of a water ionizer, all milky, and say then that the hydrogen can be C after all. Or they hold a lighter to the water outlet of the device and there are small explosions. Or if you look at one of these small hydrogen boosters with a PEM cell, there you can see how more or less bubbles move through the water and appear to dissolve. Then, on the other hand, there are people that say it depends on the size of the bubbles that they dissolve in water. What exactly happens there when hydrogen dissolves in water? And can the hydrogen be seen?
Often I get a question about the hydrogen gas dissolved in the water, because with some of these products out there, when they make their hydrogen water, they see just tons of gases, bubbles in there. It's milky white, it's foggy, you see all these gas bubbles. Does that mean the hydrogen, what does that mean? Does that mean that there's so much hydrogen in there that it's super saturated and the gas is just coming out? Or what's going on? Is this a good sign? Well, if you see the gas bubbles in there, you know that hydrogen is being produced. But if you see the bubbles, those bubbles you see is the gas that is not dissolved, and really is not going to offer you any benefit because it's not in the water. It's just, when you see bubbles, microbubbles, they go through two things. Either they're gonna go in, they're gonna continue shrinking until, and the gas molecules go into the water until it dissolves, or they'll coalesce together and get larger and then evaporate out of the water. So those are the two options when you see that. So when you see those big macro bubbles in the water, well, it's not dissolved in the water, so you don't know what the concentration is. And in fact, I've seen you can make water that is so foggy it looks just like milk, and then when you go to measure the concentration, assuming that's going to be really high, you can't even measure 0.1 ppm. So just because something has tons of bubbles and it's milky and it's foggy and everything does not mean that the hydrogen has actually been dissolved in the water. It just means that there's lots of bubbles there. So you actually still have to measure the concentration of hydrogen, because it is the unseen bubbles, if you will, that matter, not the ones that are seen. And this is similarly, there are various devices where you can light a lighter, for example, and hold it underneath where the water comes out, and you can hear the sparks, and it's crack, crack, crack. And that's a great demonstration showing that it really is producing hydrogen. But it's a very big difference between producing hydrogen and dissolved hydrogen, and the therapeutic benefits come from the dissolved hydrogen. So really that's just showing that you have hydrogen that's not dissolved in the water. Now you may have hydrogen that's also dissolved in the water, but again you'll have to test that. So just because it's making cracking sounds doesn't mean anything. I mean, you could even put the argument that a machine that makes water with no cracking is more effective because all the gas ends up getting dissolved into the water instead of being wasted into the atmosphere. You know, it's all marketing stuff, if you will. But point is you need to actually measure the concentration of hydrogen in the water, and can't just look at something and say, yes, it's foggy, yes, it's milky, yes, it makes a cracking sound, and therefore has hydrogen. We don't know that. The gas dissolution takes time. In our body, for example, we dissolve carbon dioxide in our blood very quickly, and it has to get out of the blood. We exhale it, and it has to happen very rapidly. And that's why we have an enzyme called carbonic anhydrase to do that, so it can dissolve the gas very quickly and release it very quickly. If we didn't have that enzyme, which works very, very fast, one of the fastest enzymes there are, if we didn't have that enzyme, we would die so quick, because we would not be able to dissolve the gas into the water or release it out of our bloodstream. And so again, with hydrogen gas, it's got to dissolve in the water, and it doesn't just happen by just simply bubbling. It takes time to reach that equilibrium.
What type of water is best suited for producing hydrogen water? Is it rather mineral-rich water, or the opposite, RO water, also known as reverse osmosis water?
So I'm often asked also which water is the best to make our hydrogen-rich water. And it's a very difficult question, because it depends on how you're making the hydrogen water. Do you just have a tank of gas and bubbling it into the water, or do you have a machine? What kind of machine is it? All these different things. It depends. For some machines, the electrolysis process, you only use like doubly distilled water, very pure, no ions, because the membrane itself is the electrolyte, and that's how that works. Other things, you have to have electrolyte in there, and so the more minerals you have, the better conductivity, and the more effective you're going to be able to make your hydrogen gas. So there's so many variables in it when it comes to that. All I can say is you can measure the concentration of hydrogen with your device. You can measure the concentration of hydrogen to see what's going to work better. You can check with your company or manufacturer and see what they recommend, if it matters at all. And then if you just look at water quality in general, drinking water with minerals in it is good for you. The minerals are very bioavailable. It's one of the best ways to get minerals, and there's been very large epidemiological studies showing that water that contains minerals in them is good for your health. It's a great way to get minerals from your source water for your dietary needs. So RO water is not toxic for you. It's, even though people say, well, it's acidic or something, it's not a dangerous acid. It's not a buffered acid or something where it can really harm you. it's lacking minerals, and your body needs minerals, but it's not going to be a big issue. But it could be wise to drink mineral water. I think there's sufficient evidence to suggest that drinking water rich in minerals is a good option for you, but certainly not required for life.
I would like to have a couple of technical questions explained about the different electrolysis devices which can be used to produce hydrogen water. One is the most interesting. There are the new PEM cells and the multiple cells of water ionizers that have been longer on the market. Can you explain the difference?
So when it comes to the field of electrolysis to make hydrogen for medical or therapeutic use, there are a number of ways to do it. You have your conventional electrolysis chambers that have no membranes, that just have an anode and a cathode. Hydrogen produces the cathode in electrolysis, and oxygen and octane is produced the anode, and the water's all mixed together, and there you have it. And then there's units that have a special membrane between it that acts like the salt bridge, and it prevents the mixing of the cathodic water from the analyte water, and that's how water ionizers that make alkaline and acidic water, that's how they work, is they have that membrane and it separates the two. And then there's other membranes that use a PEM or a proton exchange membrane that allows only the protons, the H plus ions, to migrate in between, and then those protons get to the cathode and produce hydrogen gas. So then there's different ways to assemble these types of chambers into a hydrogen water product. For example, with this use of the SPE or solid polymer electrolyte using this PEM membrane style, you could make the pure hydrogen gas, and then it's just pure hydrogen gas that's made at the cathode, and then the hydrogen gas is then infused into the bulk drinking water and should go through some sort of dissolver or dissolving mixture of some sort, so it actually gets into the water. So those are the two methods of electrolysis that's being used to make hydrogen gas. Which one is better? Well, it depends on how good the design. The best design of another is always going to be better than the worst design of the other, right? So again, you can simply measure the concentration, and then there's other things to look at. Are you going to have calcification and scale issues with this? Do you have to use this special water or not? Or do you run the risk of having electrode degradation? You have to have the purest electrodes, or are you going to have metal particles that get into the water could be harmful for you? There's so many questions to consider when looking at all of these things, and it's still a new field of work that's being developed right now.